So, welcome to this last lecture on finite element formulation of ductile fracture in coupled thermo-elastoplastic dynamic contact problem. So, in today's lecture, we will discuss the thermal formulation, the contact formulation, we will see some validation problems, finally, some results, and then we will conclude this course by discussing what we have covered and what we have not covered. So, in today's lecture, we are going to cover following 5 topics. So, till last lecture, we had covered the finite element, finite difference discretization for coupled thermoelastoplastic problem. Now, during that discretization, we had treated temperature to be at time t. So, how do we calculate temperature? So, for this, what we have to do is, we have to do the incremental heat conduction analysis to determine the temperature rise. Now, in impact problem, you will have heat which is generated at the contact surface because of the contact friction. So, in elastoplastic problem, you also have heat generated because of the incremental plastic deformation. So, now you have two different ways in which the heat is generated in the system. One is because of the plastic work which is taking place, and then the other is because of the frictional heat which is generated at the contact surface. Now, these two heat generation have to be taken into account. So, in this section, we describe a finite element, finite difference formulation for a 3-dimensional transient heat conduction problem. So, first we will present the governing equation, followed by expression for the heat generation due to plastic work and frictional heat, and then we will use the Galerkin method for finite element discretization, and then we use the finite difference scheme for solving a system of ordinary differential equation which is of first order. So, in previous chapters we had a second order ordinary differential equation, now we will have a first order ODE. So, the governing equation for a 3-dimensional heat transfer equation in Cartesian coordinate is given by following equation. So, this is called the Fourier's law, and here your K is the thermal conductivity, T is your temperature, Q dot is the internal heat generation per unit volume per unit time. So, this is the heat generation because of the plastic work. Rho is the density, C is the specific heat. And this dot over T denotes derivative with respect to time. So, if you write explicitly, you can write equation 115 in following form. Now, we assume that these material properties do not depend on temperature for simplicity. However, they can be taken function of temperature. That would be more realistic, but then this adds a lot more complication into the analysis. So, right now what we will take? We will take these material properties independent of the temperature. So, that means K can be taken out here. Now, the heat generation term Q dot due to the plastic work is given by beta by delta T integral T to T plus delta T sigma contracted with the incremental plastic strain. So, this you can write sigma d epsilon PL. So, this is a plastic work that is being dissipated, and a bulk of it roughly 90% of it. So, this beta is a factor which says how much of plastic work is getting converted to heat, and experimentally people have found that this beta lies in the range of 0.85 to 0.95. So, here in all the simulation that will show, we will take beta as 0.9. Now, the heat generation due to the friction is taken as Q dot F and it depends on the shear stress at the contacting surface and also the relative tangential velocity V s. Okay. So, absolute value, it depends on the absolute value, it does not depend on which direction there is a slip. If there is a slip, there will be heat generated, and then this rho is, is taken as a function of the effusivity of the two materials in contact. Okay. So, this is not rho, I mean let us say this factor is E upon E 1, E 1 upon E 1 plus E 2 for first body, and E 2 equal to, I mean rho 2 equal to E 2 upon E 1 plus E 2, and E 1 is root over k by rho c, k 1 rho 1 by rho c, and E 2 is root over k 2 rho 2 by c 2. Okay. So, 1 denotes body 1, 2 denotes body 2. Okay. So, part of the heat which is generated at the contact surface will go inside the one body, the part of the heat which is generated is assumed will completely go inside the other body. Okay. There is no heat which is getting dissipated to the surrounding environment. Okay. That is what we assume. Okay. Now, to complete the given differential equation, we need what is called the initial condition and the boundary condition. Okay. So, the initial condition is specified by specifying the initial temperature T 0 of the body as a function of spatial coordinates. So, at time t equal to T 0, the initial temperature field is T 0, and then on the boundary we have some temperature boundary condition specified. So, certain part of the boundary may have temperature which is fixed. So, let that boundary be denoted by del omega 0, and at those boundaries temperature will always remain T s, where T s stands for the prescribed temperature and it is as a function of the boundary coordinate. Now, at the certain part of the boundary del omega 1, there will be heat which is coming inside the body. So, heat flux is Q star is received on the boundary del omega 1, and this is specified by following condition. K del T by del x into N I equal to Q star. Here x I mean spatial coordinate x. And then N I is the component of the unit outward normal vector on the boundary del omega 1. So, this Q star represent the heat flux due to frictional heat generation at the contact surface. So, that is how we will take into account the frictional heat. And also, if your problem is such that convection also becomes necessary to take, then we also have the convection boundary condition given by equation 122 at boundary del omega 2. Here we assume that H is the convective heat transfer coefficient and it is independent of the temperature, and T infinity is the ambient temperature which always remains constant, and T is the boundary temperature. And this negative sign is chosen because heat is transferred to the surrounding. We assume that T will be greater than T infinity, therefore, the heat goes outside the boundary. Now, we develop the weak form first, and for weak form what we do? We multiply equation 116 by a weight W. So, we multiply by weight W and integrate over the entire domain of the problem omega. So, W is the thermal weight function and it satisfies the homogeneous version of the temperature boundary condition, and omega is the domain for the thermal analysis. And now, you do here you do integration by parts, and then you use the Gauss divergence theorem. So, equation 123 can now be written in the following form, and then this is, so it will, this is decomposed into two terms, one is here and the other is here, and these two terms remain as it is. Now, you can split this boundary integral into three parts. One which is the boundary del omega 1, other is del omega 2. So, this is where your heat flux is there, this is where your convection boundary condition is there, okay, and one where your temperatures are specified. So, where temperature are specified, you will have W equal to 0 at the temperature boundary condition. So, instead of 3, you will finally have 2 surface integrals, and then if you substitute from equation 119 and 121, you will get on del omega 1, you will have this term equal to k T comma I N I will be Q star and k T comma I N I will be H T minus T infinity. Okay. So, this is the second term. Okay. And then this is your weak form. Okay. So, you have reduced the continuity requirement on the approximation of T by one order, and then what we can now do is we can discretize the domain into a number of finite element, and the temperature T and the weight W over a typical element can be approximated using equation 127 and 128, okay, where n is the shape functions corresponding to the element that you have chosen, and T corresponds to the temperature at the elemental nodes. Okay. Now, if we choose an 8 noded brick element, then you will have 8 temperatures at 8 nodes and you have 8 shape functions. Okay. Therefore, you can write the derivative of temperature with respect to spatial coordinate x like this, okay, and the time derivative of T can be written like equation 131, and the gradient of W is obtained like this. Okay. Now, the heat generation, okay, per unit volume, per unit time can be written in terms of the heat generation at the nodes, okay, by usual this kind of discretization. Okay. And once you substitute all these approximations, okay, so if you substitute all these approximation here, okay, so equation 127 to 135, if you substitute in equation 126, then you will get following form. Okay. So, once you have this following form, here we have used matrix vector notation. Okay. So, where we have used the boundary. Okay. So, at the boundary we have to use T equal to N B transpose T B, where T B contains the nodal values of T over a typical area element. Okay. So, remember, say for a 8 noded element which lies on the boundary. So, at the surface, so if this is the bulk on the surface, you will have only 4 nodes. Okay. So, therefore, the boundary temperature will be only consisting of these 4 nodes. Okay. So, that is what you have to see here. Okay. So, all this here represents the boundary. Okay. And here TIB stands for the unknown temperature of node I on a typical area element. Okay. So, now I can further simplify equation 136 by following these notations given in equation 138 to 140. Okay. So, here C, Kk and Kh are called the specific heat matrix, elemental conductivity matrix and elemental convection matrix. And if you use this in equation 136, you will get equation 137. Okay. So, you will get summation over all the elements, the specific heat matrix term, okay. You have the Tenvin matrix term and you will have the convection matrix, okay. You have the heat generation matrix, okay, like this, and then finally, the heat generation vector, the heat flux vector and the elemental convection vector are defined using equation 141 to 143. Okay. Now, the only job is you assemble these elemental quantities over all the surface and the bulk elements, and you get what is called the global equation after the assembly as C T dot plus K T equal to Q. Okay. So, equation 144 represents a system of coupled linear first order ordinary differential equation. Okay. So, T here is a global temperature vector, T dot is a global temperature derivative vector, C is a global dynamic coefficient matrix, now the global specific heat matrix, K is the global static coefficient matrix, and Q is the global right hand side vector. Okay. Now, this is a first order linear ordinary differential equation, and to solve this what we have to do is we have to discretize this time derivative of temperature. Okay. For this we can use again the finite difference scheme. Okay. And here what we do, we use what is called the direct integration method. Okay. So, remember time integration are of two types. Okay. So, there are direct time integration schemes, and there are modal methods. Okay. So, modal methods are usually favored when you have lower eigenmodes, and direct time integration scheme works for all cases. So, we use direct time integration, and for this we have to use an appropriate finite difference scheme. So, in this particular discussion we use the following finite difference scheme. Okay. So, 1 minus gamma times the rate of temperature at time t plus gamma times the rate of temperature at time t plus delta t is roughly equal to the difference of the temperature at t plus delta t and time t divided by delta t. Okay. So, that is the approximation that we use. Okay. And then like the Newmark's method for structural dynamics, equation 145 also contains a parameter gamma that can be chosen to obtain a desired accuracy and stability. Okay. And at the end of this particular section, we will see what are different values of gamma which are commonly chosen. Okay. So, now what we do is we write equation 144 at time t. Okay. So, our equation 144 was C dot plus K T equal to Q. So, we first write this equation at time t. Okay. I can write this as time t, and then I can also write this as time t plus delta t. Okay. I can write t plus delta t, t dot plus k t plus delta t equal to t plus delta t q. Now, I have two equations. I multiply this equation by 1 minus gamma, I multiply this by gamma, and I simply add these two. So, this is the first equation, this is the second equation, and I just then eliminate the rate of temperature T dot and T plus delta T dot from equation 146 and 147 using this equation over here. Okay. So, if I add these two terms over here, you see I will have 1 minus gamma into T plus delta T T dot and plus gamma times T plus delta T dot. Okay. And this is nothing but this term over here, then that I can substitute. If I do this, finally, I will get C plus gamma delta T k into the vector of temperature at time t plus delta t equal to C minus 1 minus gamma delta t k, okay, into the temperature at time t plus gamma delta t into the vector q at t plus delta t plus 1 minus gamma into delta t, the vector q at time t. Okay. So, I basically will know my heat generation at t plus delta t, because at that point I would have computed my displacements, I would have computed my stresses in the plastic strain, and using those updated values I can compute t plus delta t q, and then I can find out C k, I know my delta t, I can set my gamma, and then I can, and I also know the temperature at the previous time step, I can directly compute my t plus delta t using following equation 149, okay, where A is given by this and B is given by this. So, this is a set of linear algebraic equation which can be solved by Gauss elimination method. Okay. Now, here what we have assumed, we have first solved the mechanical problem using a particular temperature once, and at the end we have got our stresses at time t plus delta t and plastic strains, okay, at time t plus delta t. And using this I can now solve my thermal problem, okay, and then I can get my temperature t plus delta t. And then I have to iterate between these two till I get a final convergence where both of these are not changing. If my time step is very small, then I can do within one Newton-Raphson iteration, I can once solve this and once solve this, and that should be enough. But if the time step is very large, then I have to do the iteration between these two mechanical and thermal problems. Okay. So, now there are different values of gamma that one can choose. If you choose gamma equal to 0, you get what is called the forward difference or the Euler method, and this is an explicit method which is only conditionally stable. For gamma 1 by 2, you get what is called the Crank-Nicolson or the trapezoidal rule, and this is unconditionally stable. Gamma 2 by 3 gives you the Galerkin method, and gamma 1 gives you the backward difference method. The last three are all unconditionally stable, while the first one, gamma equal to 0, is the conditionally stable. It depends on delta t that you choose. Okay. So, once we have completed our thermal formulation, our final job is to do the contact formulation. Now, all the derivation that we have done till now, it is for two body contact problem, and what happens at the contact surface, we neither know the displacement and we neither know the forces. So, what happens? We have more number of unknowns than the number of equations. So, we have to generate some extra set of equations, and these extra set of equations will be generated using the contact formulation. Okay. So, in contact, rather than discussing in detail about the contact formulation, what we will do is, we will just look into some of the essential features of contact, okay, and we will discuss the Lagrange multiplier method in a brief sense, okay, because contact itself is a very big subject which requires itself a whole course on contact formulation, which I am not doing here. So, but I will give you the basic idea. Okay. So, now the first we have to write what is the contact conditions. Okay. So, the primary physical requirement of a contact problem are impenetrability of bodies, compressive interaction between the bodies, and contact friction. Okay. So, if you are at the macro scale and you are not at a very small scale where the adhesion comes into picture, in that case if you are solving the contact problem, non-adhesive contact problem, then the interaction between the bodies can only happen if the tractions between the bodies are compressive in nature. Okay. If you go to adhesive contact problem, then there can be tensile tractions also. Okay. Now, this is one important thing. The other is impenetrability, which means that during the entire course of simulation or the contact, one body cannot penetrate the other body, that is physically not possible. Okay. So, the impenetrability condition means that the interiors of the domains of the two bodies cannot overlap. Okay. So, if you have one body over here and you have the another body over here, okay, and this is volume 1 and this is body 2. Okay. So, this one donates body 1, 2 donates body 2. So, this body cannot penetrate this body and this body cannot penetrate this body. So, mathematically you can write the intersection of the volumes of the two body is a null set. Okay. So, this is the condition that you have to satisfy. Also, on the other hand, the material points on the boundaries may coalesce during the motion of the bodies. Okay. So, during contact, this part of the boundary say, okay, so the top is T S1 and this is T S2. Okay. So, now the two bodies can have a common contact surface called SC. Okay. So, the intersection of the surface of two bodies, okay, so this is the Okay, so this C. So this is the entire surface of body 1, this is the entire surface of body 2, and if you take the intersection of these two, you will get what is called the contact surface, and this is not null surface. So the volumes, intersection of the volume gives you the null set, while the intersection of the surface gives you the contact surface. Okay. Now, in the derivation of the expression for the contact condition or contact forces, it is convenient to choose one contact body as hitting surface, while the other as the target surface. Okay. So, when you do contact analysis, one body is always chosen as the hitting body and the other body is chosen as the target body. Okay. So, this is also called the master body and this is the slave body. Okay. And the current position of the target surface defines the boundary of an inadmissible region for the current position of all hitting points. Okay. So, the points on the hitting surface lying exactly on the target surface are said to be in contact. Okay. So, we can choose body 1 as the hitting surface and body 2 as the target surface. Okay. Now, before we proceed with the contact simulation, we have to define what is called the local coordinate system, okay, for the derivation of the contact expression. Okay. So, contact conditions are described with the help of set of unit vectors attached to the contacting surface. Okay. So, at each contacting point you have to define a set of unit vectors, okay, which are normal and tangential to that point. Okay. So, assuming that the hitting surface is smooth everywhere such that an outward normal donated by n 1 1. Okay. So, this n hat 1 1. So, this one shows body 1 and the superscript 1 shows body 1 and subscript 1 shows the direction. So, the one direction is always taken as the normal direction. N hat, so hat shows it is a unit vector and t denotes here that it is at time t. It is calculated based on the configuration of the body S1 at time t. Okay. And this is defined at each point x1 which belongs to body surface body 1. Okay. Now, two orthogonal tangential vectors n2 and n3 are chosen such that the cross product of n2 and n3, okay, gives you the normal. Okay. So, at the contact surface, okay, you can define, okay, what is called the normal like this and two tangential vectors like this. Okay. So, n2 cross n3 gives you the normal vector n1. Okay. This is set by the right hand rule. Okay. So, if you curl your fingers from this to this, then the direction of the thumb will give you the normal. Okay. So, this is the convention that we follow. Therefore, similarly, a triad of vectors, normal vectors n1 2, n2 2 and n3 2 can be defined for the corresponding point x2 on target surface. Okay. Now, if the two boundary points x1 and x2 are in contact, then the unit vectors, okay, satisfy the following condition. Okay. So, they are equal, but opposite in sign. Okay. Now, the impenetrability condition and the compressive interaction and the friction law are described with respect to these coordinate systems. Okay. Remember, all these impenetrability condition that mathematically you will derive, the compressive traction, okay, everything have to be described with respect to these coordinate system. Okay. So, normally you will have those traction with respect to the global coordinate system, but then you have to transform those vectors to the local coordinate system defined by these normal and tangential vectors. Okay. So, you can use the concept where they discuss in our discussion on tensors, where how to transform one tensor from one coordinate system to another coordinate system. Okay. Now, mathematically you can express the impenetrability condition using what is called the gap function. Okay. So, now this is your target surface, okay, target body, and this is your target surface, and let the point which comes in contact on the target surface have the coordinate x2, and the point on the hitting body which comes in contact with the target point, let its coordinate be x1. Okay. So, then this vector over here will be nothing but x2 minus, okay, this from A to B, okay, let us say this is P. So, T p plus T x 1 will be T x 2. Okay. So, T p equal to T x 2 minus T x 1, and then if you take a dot product with the normal in this particular direction, you will get the penetration. Okay. So, this is your normal, and if you take the dot product of this penetration with respect to that normal, you will get the component along the normal direction, and this is called the gap function. Okay. So, this is the penetration that can happen, and from the impenetrability criteria, this penetration always has to be equal to 0. Okay. So, when you are writing the code, you always have to ensure that this gap function turns out to be 0, and this gap function for every point A, it is used to find out the corresponding point B on the target surface on which point A will come in contact with. Okay. So, that is where the gap function is usually used. That problem itself is a nonlinear problem which is solved locally at each contacting point using Newton-Raphson iteration. Okay. Now, in the tangential direction. So, this was along the normal direction. Now, what happens in the, let us say, in the tangential direction. Okay. So, if this point is contact within this point, then depending on the tangential traction, the body may slip or the body may stick. Okay. So, if the two boundary points are in contact at time t, then from the Newton's third law, you would know that the traction, okay, the contact traction at the contact point are equal and opposite. Okay. So, for normal component of the stress vector at the contact point to be compressive, the following conditions have to be satisfied. Okay. So, if the contact traction have to be compressive, then the normal tangential vector dotted with the normal vector on body n, okay, should be less than equal to 0, and hence for all time t, if the traction is less than equal to 0, the 2 points will remain in contact. If this traction T 1 n becomes greater than 0, then we say that the body has gone out of contact. And in the tangential direction, you can find out respectively the tangential tractions T 2 and T 3 by taking the dot product of the traction T n with the tangential vectors n 2 and n 3. Okay. And then if the resulting traction, okay, so this is the resulting traction root over T 2 square plus T 3 square, and that gives you the tangential traction, and if this tangential traction is less than mu times the mu f times the normal traction, then you have what is called the sticking condition, then the two bodies cannot move relative to each other. However, if T t becomes greater than mu times T 1 n, then T t should be equal to mu T n, and the body is said to be in the slipping condition. Okay. So, in the tangential direction, you again have two ways, I mean two conditions, either the body may stick if this is less than equal to mu times t, or it may slip. In that case, T t is greater than this, then T t has to be set equal to mu T 1 during the numerical simulation. Okay. So, these two conditions can be written in the following penetrations in the tangential direction in the following equation form. And then once we have set up the penetrations and the impenetrability criteria, then we can use one of the constraint handling techniques available in contact mechanics, okay, computational contact mechanics. There are penalty method, augmented Lagrange multiplier method, Lagrange multiplier method. So, we use what is called the Lagrange multiplier method, and for that the kinematic constraint for a contact point is given by following equation, and for a slipping point we will have the following equation. Okay. And these when we assemble, okay, for all these sticking contact point we will get this final form. Okay. So, this is a very long derivation. So, I am just giving you the final expression. Okay. And for a slipping contact point we will have this particular form. Okay. So, you can assemble these globally and you can get the following global form. Okay. And here you notice that we do not know part of the right hand side vector, and also we do not know the part of the, I mean this is obviously the contact displacement and the contact reactions are not known. Also we just know P from the geometric consideration. Okay. So, what we do is we add this equation with the equation that we get from the Newton-Raphson iteration to eliminate the reactions corresponding to the contact node. So, this is a global unbalanced force vector corresponding to the contact nodes, and this when we add with the Newton-Raphson iteration we can eliminate this over here, and then you will get the tangent matrix K of two bodies here. In that case you can solve for the unknown contact displacement and the contact forces. Okay. So, what is the algorithm for dynamic large deformation thermoelastoplastic contact problem? Okay. So, the first step is find the potential contact nodes for which the hitting and target nodes are closer than a prescribed length. Okay. So, when you start a simulation, one body is already a master's body, the other is a target body, and then within a prescribed length from the master body you check master surface, you check whether there are some nodes of the hitting body that are coming in contact. And then what you do, you can, and this step is optional, but you can do the renumbering of the nodes. Nodes of the hitting and target bodies are renumbered such that the contact nodes are numbered first, and this is carried out to facilitate the static condensation of the stiffness matrix that we discuss at the end of the finite element discretization to in reducing the computational time. Okay. Now, we form the coefficient matrix and the right hand side force vector based on the current geometry, state of stress, and the condensed form of the effective stiffness matrix and force vector are formed, and then we form the Newton-Raphson iteration. So, this here corresponds to the modified Newton-Raphson scheme, because the effective stiffness matrix is formed outside the Newton-Raphson iteration. Okay. First, what we have to do once the Newton-Raphson iteration start, we do contact search. Okay. So, this step is called the global contact search. Okay. So, here we are more interested in whether a node is coming in contact or not. We are not interested where it comes in contact, we are just interested whether it can come in contact or not in the current load step. Okay. Remember, this is for one particular load step, okay. One particular delta t, from t to t plus delta t, this is what we are discussing. So, now you do what is called the local contact search. Okay. You search for the target segment corresponding to each hitting node. Now, I am more interested in where does my hitting node exactly come in contact with the target segment, which target segment and which location. Okay. So, we can use what is called the master slave algorithm. Okay. And then we start the contact iterations. Okay. So, we assume that all contact nodes are in the sticking friction condition, then the contact stiffness matrix and the right hand side vector are formed and combined with the condensed form of the effective stiffness matrix and effective force vector, and this system of equation is then solved. Then we find out if there are some out of contact node for which the normal component of the contact reaction is tensile. This may happen as you update the contact reaction, some nodes may go out of contact and some nodes may come in contact. Okay. So, the contact reactions at these nodes are set to 0 during the subsequent contact iteration. Then we remove all the out of contact nodes, the nodes which are slipping are determined. Okay. After we have done this, and we know that if the node slips, if the contact reaction at that node violate equation 159, which is the tangential traction is greater than equal to mu times the normal traction T n, then I know that my node is slipping. So, I determine which are the nodes which are slipping. There I have to set my tangential traction equal to mu times normal traction T n. The contact iterations are repeated till the correct direction of the friction force is obtained for all slipping nodes, and the status of all contact nodes does not change. So, we have to do these iterations till there are no nodes which are going out of contact or are not coming in contact, and the status of all the sticking nodes or the slipping nodes remain as it is. Once this happens, we will say that our contact iterations have converged. Okay. Once we have found out the contact displacement, this is where we have found out the contact displacement and we have found out the contact forces. Once we have found that, we can find out the displacement of non-contact nodes from the displacement of contact nodes, which are called the type 2, type 1 node also. This is done using static condensation scheme, and then we apply what is called the radial backward return algorithm using new objective stress measure. Okay. So, this we have already discussed. We find out the stresses, and from these stresses we find out the what is called the internal forces. Okay. And then I can find the unbalance. Okay. So, I can do the first updation of stresses, strain and the contact forces. I can find out the internal forces corresponding to the stresses, and I can find out the unbalanced force vector, and I can check for the convergence. If the Newton-Raphson iteration has converged, then we print the results at the end of the increment and we move to the next time increment. Okay. And if the convergence criteria is not fulfilled, then the Newton-Raphson iterations are continued till the convergence, that is we go back to step 4 and we restart the next Newton-Raphson iteration. Okay. So, here if your Newton-Raphson method is found to be diverging, okay, then we use what is called the line search method. Okay. Here is what we use, radial backward return algorithm for integrating the incremental stress strain relation. Okay. So, now we come to the validation of the formulation that we have discussed. Why is validation needed? Any complex numerical model that you develop, okay, has to be first tested for any form of error in the modeling or in the implementation step. So, how do you test whether your formulation is working fine? So, what you do, you take some problems for the literature, either experimental or numerical, and you run those problems using your code and try to see whether the results obtained from your code and those reported in the literature, that is experimental or numerical, matches well. Okay. They may not match exactly, but they have to match pretty well, okay, say up to 10% error. Okay. So, here we have validated a lot of problem. We just take two of them. One is a static problem. It is a tensile test of cylindrical and sheet specimen. So, you see here the geometry of the tensile test. So, this is the cylindrical specimen. So, this has a cylindrical cross section, okay, and this is a sheet specimen. So, it has a rectangular cross section. Okay. So, you can see here this is the side view and this is a cylindrical specimen. And what we do? We apply displacement at the top surface, and at the bottom we keep this fixed in the normal direction. It can move in the tangential direction. Here also we keep fixed in the normal direction, it cannot go in the z direction. Okay. And then because there are no external force, therefore, I have to go for I have to apply what is called the arc length method. So, here I will use arc length method because I expect that after some time there will be necking which will happen here. Okay. So, because of the necking, the load displacement curve will have a negative tangent, and then I have to be careful because usual Newton-Raphson will not converge. Okay. So, these are the material properties. Okay. So, the Young's modulus, Poisson's ratio, the initial value of the yield stress, and the hardening coefficient and hardening exponent. Okay. So, remember our hardening law is sigma equal to sigma y 0 plus k epsilon equivalent plastic raised to power n. Okay. So, that is how my yield value is changing. So, this is the chemical composition of this SAE 1045 steel, okay, which we have taken from the literature. And we first, the tensile test results of cylindrical specimen are simulated. We only take the 1/8 of the specimen. Okay. So, we just take this. So, this is the half of the specimen. So, we just take the 1/8. Okay. So, we just take this much. Okay. So, if you can see, it is only this much of specimen is what we take in each case, and the number of finite elements are 1890, and these are the number of nodes. And then we do the simulation of the sheet specimen. Again, we will use only the 1/8 of the specimen with these many number of elements and nodes. Okay. And this is of course a static problem. So, here delta T is always chosen to be 1, rho is taken to be 0. So, that there is no mass matrix and the problem turns out to be a static problem. Now, if we have static problem, then the first thing we do is we compare the engineering stress strain curve, okay, and the ratio of the current diameter of the cylindrical specimen. So, this is for the cylindrical specimen, okay, diameter of the cylindrical specimen at current value divided by the initial diameter, and we compare our simulation result with the experimental results of Cabegaz and Celentano. Okay. So, if we do this, you see this is the experimental result and this is what the simulation result that we get. Okay. So, this is the experimental result and this is the simulation result that we get. And although there are some errors at certain positions, but then what we can say that at least our numerical implementation is pretty much okay. And you can see there is a, if you can see here, there is a necking. At this step you achieve the ultimate stress and the load drops off. Okay. So, this is where you will observe necking and then you will have a rapid degradation of the value of the diameter. Okay. So, this is the result for the sheet specimen. We compare the engineering stress versus engineering deformation and the width and thickness ratios with the engineering deformation with those from simulation and the experimental results of Cabegaz and Celentano. And again we see we are very well able to capture the trend which was observed in the numerical simulation. Okay. So, here the width and the thickness, okay, the current width by original width and current thickness by original thickness matches well with the those results reported by Cabegaz and Celentano. Okay. So, with these static results, we are sure that at least the static part of the code is working fine. So, next what we do, we try to validate the dynamic part, and the dynamic part we do using the Taylor rod impact test, for which results are already available numerically, and we do a coupled thermomechanical analysis. There is no damage here, damage is equal to 0. Okay. And we take the Celentano's numerical and experimental results. So, this Taylor rod impact problem is you have a cylindrical rod which impacts a rigid surface at a very high impact velocity, and we observe the growth of equivalent plastic strain temperature at this impact phase at point P, okay, at different time step. Okay. And we use the Newmark's time integration algorithm, and the Johnson-Cook model is used to take into account the effect of plastic strain, temperature and strain rate on the yield value. Okay. And these are the material properties, and we compare the ratio of the final length to initial length of the rod with the different impact velocity, and we compare our work with the experimental and numerical work of Celentano. We see that for 122, 163 and 244 meter per second, our results matches well with the experimental results and the numerical results of Celentano. So, we have a very nice result that we have, and this is the ratio of the radius of the rod at the impact phase, okay, divided by the initial radius. Okay. So, at the rod impact it will expand and the initial value which is 1. Okay. So, initially RF equal to R0. So, you have 1 and it will expand, and then you see we have the results matching with the results of Celentano. Okay. So, these are some of the results for the equivalent plastic strain growth at 3 points on the impact surface, and for 3 different impact velocities 122, 183 and 244, and we see our results which are in solid line and the results of Celentano. Okay, and we see that our results also match well with the results reported in the literature. Okay. So, these are the growth of plastic strain at 4 points along the impact axis, and this is a temperature rise. Okay. So, the initial temperature is 25 degree, and you see that for lower velocities the rate rise of the temperature is only around 108 degrees, while for 244 it can go up to 400 degree centigrade. Okay. From 25 it goes up to that level, and for 3 impact points our results match well with the result reported by Celentano. Okay. So, with this validation, what we can do now is we can discuss some of the results. So, the first thing is we simulate the damage and ductile fracture in tensile specimen. So, again the geometry remains as we use for the validation problem. However, the material now is chosen as ASI 1090 and 1045, for which we have the experimental results reported in the literature. So, this is the chemical composition of the 2 steels, and these are the material properties which we have taken from Leroy's 1981. So, this is 1981 results, and the damage constants in our damage growth law, which we discussed in the initial slides, are obtained as follows. Okay. So, these are used using curve fitting, and these again we use the cylindrical specimen and the pre-notched specimen. So, this is a pre-notched specimen, cylindrical in nature, and this is completely cylindrical. And for cylindrical specimen, this is the result for 1090 and 1045. You can clearly see there is a necking involved, and this black colored elements here show the fracture. So, these are the elements where the damage has reached this critical value. Okay. So, this critical value of damage means when value of D reaches 0.6 for 1090 and 0.5 for 1045, I say that that particular element has lost its stress carrying capacity, and then the stiffness is set to a very small value, and that is blackened. So, this is the fracture. So, clearly for 1045, which is more ductile, you can see the cup cone kind of fracture, while 1090 is a much more brittle kind of thing, you have a flat surface. Okay. And from the experimental results reported by Leroy, I compute the numerical result for damage and versus the equivalent plastic strain at the center and at the outer surface, and match with the experimental result. And you can see our numerical results match well with the trend for the numerical results of experimental results of Celentano for both 1090 and 1045. Okay. So, you see that at the outer surface the damage growth is very slow, while at the center it is much more faster. So, this is also observed in the literature that the crack will initially start at the center and propagate towards the outer surfaces. And you can see for 1090 it is more or less the crack will occur all throughout the center surface, but for 1045, which is much more ductile, it will occur at the center much more earlier than at the outer surface. That is why it leads to the cup cone fracture. Okay. Again, this is the load displacement graph for the 1090 and 1045, and you can see you have a sharp drop in the load once the necking starts and the damage reaches a very high value. Therefore, you need arc length method here to solve these kind of load displacement curve. Here, because your tangent, okay, the tangent matrix will become singular. Okay. So, you need some arc length method. Okay. So, this is the growth of damage versus plastic strain at the center and outer surface for different values of plastic strain. Okay. So, let me just skip. Now, we simulate the damage and ductile fracture in the Taylor rod impact test. Okay. So, we take the geometry as we discussed in the validation, but now we take a material which is 1045, and for that we use following Johnson-Cook formula, for which the material properties are given okay, here, and they are obtained using the tensile testing. and then this geometry of the Taylor rod is shown in slide 89, and the finite element mesh consists of 12,000 elements and 12,120 nodes, and the time step that we have chosen is 0.05 microsecond. So, this is a very high impact velocity problem, therefore, we choose a very small time step. So, there are two kind of failures that are observed in Taylor impact test. One is called the tensile splitting. So, at 300 meter per second impact, you can see that at the impact phase you have a mushrooming, and also you have fracture which occurs at the 4 corners. Okay. And if you measure this kind of result with the experimental result, you see in the experimental results of Woodward et al. Also there is tensile splitting which occurs at the outer surface, while the inner surface is more or less outside of that, there is no visible fracture. Okay. So, we observe tensile splitting for lower impact velocities, which is also observed in the literature. And for higher impact velocities, say 400 or 500 meter per second, experimentally people have observed that you have fragmentation. Okay. So, you have some small parts at the outside surface which come out, and at the middle there is a huge chunk of a material that comes out. Okay. So, here also for lower impact velocities, you can see at the center there is some damage, and also at the outer surface there is some damage. Okay. So, they are same view. So, this is actually at the other side. Okay. And for higher impact velocity, you can see that at the middle there is a huge chunk like this here. Okay. This is a chunk like this here, and in the outer surface you will have chunk like this here. Okay. So, again the numerical simulation is able to capture what is called the confined fracture, fragmentation and separation of conical zone. Okay. So, this conical zone and this is fragmentation which are coming out. Okay. So, with these numerical results, we come to the end of this course, and we have some closure remarks on this course. So, to summarize this course, we have discussed in detail tensor and tensor analysis. We did this only for the Cartesian, okay, but for non-Cartesian we did not do it because it was not possible, but with kinematics and kinetics that we discussed was very general, that you will find in a course on continuum mechanics also. We did a detailed derivation of the constitutive relation for a compressible neo-Hookean material. Okay. We did very detailed derivation so that you could understand. We also did a very detailed derivation of the finite element formulation and various solution strategies. Okay. What we also discussed the application of computational continuum mechanics to the dynamic ductile fracture. Okay. Although we did very detail in this hyperelastic material, but for the sake of completeness, we also discuss in detail a little detail about the dynamic ductile fracture, where elastoplastic effect, thermal effect, strain rate effect and the damage, everything comes into one particular simulation. So, we did one kind of multi-physics problem. So, what more you can do? Non-Cartesian tensor analysis you can study by yourself if you want. You can refer to some books. I can give you reference to some books if you are interested. Continuum thermodynamics is not what we discuss. This is discussed mostly in the course on continuum mechanics, not in this applied course, and also the constitutive relation derivations. Okay. For example, from the given Helmholtz free energy or the Gibbs free energy potential, how to derive the constitutive relations, that we did not discuss. We directly took a material model which is Neo-Hookean material model. So, this also can be done in a course on continuum mechanics. Okay. And additionally, we can do incompressible Neo-Hookean material models and their finite element formulation. So, incompressible means there will be no volume change and there is a condition J should be equal to 1, and so all the deformation should be such that J should come out to be 1. This kind of constraint we did not study in this course, but obviously if you are interested you can go into the references and look into this. Okay. So, with this we will come to end of this course. Thank you very much.